You ask a model even to write a poem. Sometimes it's brilliant, sometimes it rambles and gives you useless results. Same prompt, same model, different answers. Why is that? To answer that, you need to know that whenever LLM writes something to you, it rolls the dice. Today we will explore how that randomness works and how 3 little settings decide whether your model writes like a poem, a scientist, or a chaos machine. When a model finishes training, it doesn't know the right answer. It only knows the probabilities. If the input is sky is, the model might predict blue, clear, bright, falling with these probabilities that you see in the screen. These are next token probabilities, but which one do we pick? You may answer, we could always take the highest probability, but then the model would repeat itself endlessly. It writes predictable dull text. So instead, we sample. We choose probabilistically, not deterministically. That's where temperature, top K, and top P come in. We want the model to sound like a human, sometimes precise, sometimes creative, and always coherent. Sampling lets us control that balance. Too much randomness can cause the model to drift. Too little, and it freezes. It becomes conservative and doesn't give any new information to us. Let's start with the simplest control, temperature. Temperature controls how flat or sharp the probability distribution is. Mathematically, we divide the logits by temperature T. Logit means that the raw output that the neural network gives you before you make it normalize into the probabilities. You don't need to understand the math here, but what is important for you is the value of the T or as a temperature. If T is equal 1, it's kind of normal sampling. If T is less than 1, you make your sampling more sharper, means that your answer will be more deterministic. If the value of T is more than 1, you will sample softer, which means that you allow more randomness in your answer. For example, if T is equal 0.7, the model becomes focused. It picks safe and sensible words. If T is 1.5, the model becomes adventurous. It starts exploring unusual options. Temperature basically doesn't change what the model knows. It just changes how boldly it expresses itself. In the next step, we want to apply a filter. We call it top K. Instead of sampling from all 50,000 possible tokens, we keep only the K most likely ones and we set all the rest to 0. Then we renormalize and pick from that smaller pool. For example, if K is 5, we only consider 5 most likely tokens. If K is 50, we allow more creativity in our variants. Top K is like telling the model stay within the reason, but you can still improvise. It prevents rare nonsensical words from sneaking in, but it still keeps the language alive. Now for the elegant cousin of top K, we have top P sample, also called nucleus sampling. Instead of choosing the fixed number of tokens, we choose the smallest set of the tokens whose combined probability exceeds the threshold of P. For example, if the P is 0.9, we keep enough top tokens so their total probability adds up to 90%. Sometimes that's 3 words, sometimes 20. It depends on your dataset. It can adapt dynamically to the situation. If the model is confident, it picks from fewer words. If uncertain, it widens the pool. That's why top P often creates smoother and more natural text than a fixed top K. Let's see it in action. For example, the prompt is that the secret to happiness is something. If we are greedy, without any sampling, we can complete the sentence like, to be happy with what you have. If we have, for example, temperature 0.7 with top P of 0.9, the sentence can be like this: to find joy in small things and share it. If we increase the temperature with top K of 100, maybe we end up something like this: to chase sunset, music, and impossible dreams. Same model, different personalities, and that's the art of sampling. But what is the trade-off here? The catch here is that the more you open the randomness gates, the more risk that you take. High temperature or large top P, it can translate into more creativity, but also more incoherence. Low temperature or small top P, it leads to more precision, but also more repetition. The key is the balance. That is why chat models use carefully tuned values like T is equal 0.7, P equals to 0.9 to sound smart and spontaneous at the same time. In real inference pipelines, we often combine all 3 together. temperature, top K, top P, and the sample at the end. This layered architecture gives developers more control on how model behaves, from factual Q&A to imaginative storyteller. It's not part of the training. It's purely a generation strategy, but it shapes how we experience the model. So you need to be careful. We are talking about the output of the model, not the training data. So when you chat with an LLM, it sounds thoughtful, funny, or weird. Remember this. It's not the mood. It's purely math. Temperature, top K, and top P. Together, they can control the tension between the order and the chaos. And that's what makes the AI writing feel human. It's predictable enough to make sense, and also at the same time unpredictable enough to surprise you. We've now seen how models generate fluent text, but how do they learn to follow the instructions, to answer questions, summarize paragraphs, or act like helpful assistant? That is where fine-tuning comes in to shape their behavior beyond next token prediction. In the next episode, we will explore fine-tuning and instruction learning and how ChatGPT learned to follow you. If you have any questions or any experience with fine-tuning these parameters in your own chatbot or your own LLM models, don't forget to share it with others in the comment down below. Until the next video, good morning, good afternoon, and good evening. Bye.